Alright, the other night we talked about how to find the derivative of an inverse trig function, and we learned three specific rules for arcsine, arccosine, and arctangent. Tonight I want to speak more generally about how to find the derivative of any inverse function, whether it's a polynomial or an exponential or a logarithmic. We just want to be more general tonight. And we're going to spend the first chunk of the video just reviewing some basic properties about inverse functions that were developed earlier in your high school career, kind of a culmination of algebra and algebra 2 and pre-calc and so forth. So our first picture here on the front has a half of a green parabola, y equals x squared minus 4 here. And I said half of it, we restricted the domain so just the x values were greater than or equal to 0. And you can see that his inverse is this purple graph, y equals radical x plus 4. And one of the nice patterns graphically is that they are reflections of one another over the line y equals x, and that will be true for all inverses and their functions. And specifically, let's look at the individual points. I see a point right here. We'll start with this one, 2, 0. The inverse is 0, 2. And we could continue to play that game. We could say, well, here's 5, 3, the inverse is 3, 5, and so forth, and you could analyze each of the individual points that are on there and labeled. But the bottom line is, anytime we have a discussion about inverse, it boils down to one simple fact. We are going to switch the x and the y values, and that's what it boils down to anytime we have a discussion about inverse functions. Alright, what do we already know about inverses? The first key point I want to make is that I want you to understand that inverse functions, they undo each other basically. A good example here is the functions e to the x and natural log of x. Have you ever wondered why the zap rule does what it does? Why is the natural log of e to the x simply x? Well, there's two things happening. Whatever e does to that x, the natural log swoops in and just undoes whatever e did to it. And they essentially offset each other or cancel each other out, thus being right back where you started. In other words, you can kind of think of it like a circle effect. You start with x, e does something to it, and you get whatever. And then ln comes in and undoes whatever e did, so you're right back to where you started. Another example would be like the cosine of arccosine. Whoops, get that little rascal in there. Cosine and arccosine undo each other, and you just get theta. Bullet number 2 here, and this is perhaps one of the most important ones going forward in our calculus lesson tonight, is that if f of a equals b, then we know for a fact that f inverse of b has to equal a. That's a fact. In other words, if the ordered pair a comma b lies on f, then we know that b comma a has to sit on f inverse. Again, it boils down to what we said on the last slide. The x values and the y values switch. Alright, in my third bullet, my screen just kind of tweaked on me here. I don't know if it's going to come out just as goofy on yours as it looks like on mine right now, but I'm going to try to squeeze in this last sentence, and I'll do it in blue so it stands out. But basically what we're trying to say is that if a is the input, in other words, it's the x coordinate of f of x, then a must be the output, then that's just a fancy name for y value, of f inverse, okay? And we're going to continue to have that conversation with ourselves and just repeat that sentence over and over later in the video tonight. Again, we're not quite ready to have our calculus discussion yet. We still want to review a few things. And this big one here says, in order for two functions to truly be inverses of each other, they must satisfy a certain property. And it goes like this. If f of f inverse of x, if we perform that composition of functions where we substitute one into the other, the answer must be x and nothing else. No more, no less. It has to equal x. So if we did f of g and got x as an answer, we'd start to suspect that they were inverses of each other, and to really put the finishing touch, we'd have to go the other direction and do g of f of x. And if we got x again, at that moment we have proven that f and g are truly inverses of each other. Alright, so we're going to put that last concept to test here. And I'm going to throw two functions at you. I'm going to say, let's let f of x be 2x cubed minus 1. And let's let g of x be the monster cubed root of x plus 1 over 2. And the question is, are f and g truly inverses of each other? And what we're going to do is, this is a two-part problem. The first thing that I'm going to work my way through is I'm going to ask myself, what's f of g of x? In other words, I'm going to take this entire function right here and substitute it into this x right in here. And it would look something like this. It's going to be 2 times the quantity, cubed root of x plus 1 all over 2 cubed minus 1. And as I begin to clean this up, the first thing that you'll notice is that, yes, the cube kills the cubed root. So I've got 2 times the x plus 1 all over 2 minus the 1. And then the 2 kills the 2. And then the 1 kills the 1. And yes, indeed, we got just plain old x. All right, now I need to start that all over again. And that's the second half of the problem. Is we're now going to do g of f. See if I can squeeze this on here. G of f of x. In other words, I am going to take this entire function here, 2x cubed minus 1, and substitute it into the x that was up there. And so it's going to look something like this. It's going to be a monster cubed root. We're going to then make our substitution, 2x cubed minus 1. We got our plus 1 all over our 2. So this one, you could see the first thing that would happen is the 1's would kill each other. Coincidentally, that was the last thing that happened on the previous example. And then we would divide by 2. And then last but not least, you'd take the cubed root of x cubed and get simply x. And at that moment, we've proven that they truly are inverses of each other. All right, now it's time to get excited because it's finally time for some calculus. And here's how the rule goes. It starts off, and instead of just throwing the rule at you, I'm actually going to go through a mini proof tonight, and I think you'll gain a greater appreciation for it. So let's start with the concept that we said earlier. F inverse of x has to equal x. No questions asked. That's non-negotiable. That has to be true. What I'm going to do is I'm going to start with this concept, and I'm going to derive both sides. And as I derive the left side, I'm going to use some chain rule. Okay, so it's the derivative of the outer, leave the inner alone, times the derivative of the inner function right here. Now, I don't want my prime sign to be confused with the inverse sign, so what I'm going to do is I'm just going to say d over dx instead of my prime sign, f inverse of x. All right, what does it equal? Well, the derivative of that rascal is simply 1. Now, today's lesson is all about this term right here, finding the derivative of the inverse function. So in order to isolate that term, I'm going to grab this rascal right here and divide him to the other side. We're just going to divide him over. So we'll start to get an idea of what this crazy formula looks like. We're going to say that the derivative of the inverse function is equivalent to 1 divided by f prime of f inverse of x. Ladies and gentlemen, that is a monster formula that we're going to learn, and we're going to commit this one to memory. It's a little wild looking, it's a little intimidating looking, but by the time we practice and get used to using it, I think we're going to be all right. And I'm going to let you in on a little secret. You're probably too young to remember this TV show, but I'm going to introduce you to a quick way to remember the order, especially the order of those terms at the bottom. Well, I just had to bust out a little theme music there for the Magnum PI hit TV show back in the day, and I apologize. You guys are way too young to remember that show, but that was a favorite of mine growing up. And the point of that one is it's going to help us remember this formula here today. Tom Selleck starred in that great show, and the abbreviation for private investigator, PI, is going to help us remember the order in which these two functions are composed in the denominator. We've got our prime on the outside, and then we've got our inverse on the inside. So Magnum PI, and I think that's going to help us remember in the heat of the moment how this formula develops. Okay, we're finally ready to sink our teeth into one of these problems. So this is the first of 3 examples we're going to do. Pay attention very carefully on this one, and then when we get to the next one, I'll encourage you to pause it and try it on your own. So we've got this given function. F of x is going to be 5x minus 2x cubed, and they want us to find the slope of f inverse at the moment when x equals 3. Now, the first thought I had back in the day, I said, well, we spent a lot of time switching the variables and just finding the inverse function back in the day. Why can't I just take that given f of x, why can't I switch the variables and say x equals 5y minus 2y cubed, solve for y, and then we'll derive that and we'll be done, and I don't have to learn any new rules. The problem is isolating this y is, darn near impossible in this situation. And so the idea of actually finding the inverse function goes out the window. So in other words, what we're claiming is we're going to be able to find the slope of a function we can't even find, which makes it that much more remarkable. But go ahead and set up our formula. What we're trying to accomplish here is we want to find the derivative of f inverse, and we want to evaluate it at 3. So go ahead and get the 3 in there right now. And it'd be 1 over magnum pi f prime of f inverse of 3. Okay, so here's the wild thing, and this is probably the most interesting part, is how do we find f inverse of 3 if we don't even have a function for f inverse? Well, it goes back to those statements we made at the beginning of the video. If 3 is the input for f inverse, then it'll be the output for f, okay? Or in other words, we could say, if 3 is the x-coordinate for f inverse, then 3 will be the y-coordinate of f. So all I'm going to do is I'm going to go off to the side here and I'm going to substitute the 3 in for the y in f. And the AP has virtually promised us that the solution to that equation will be a very nice, well-behaved number. A number that's so nice that we can indeed just solve it in our heads. So what I want you to do is just start substituting nice numbers like 0, 1, and 2 in for x until you find a solution. If I substitute a 0 in for these x's here, it will not work. But if I substitute a 1 in for those x's, I do get 3 as my answer. So here's what I'm now claiming. I'm claiming that f of 1 produces a 3, therefore f inverse of 3 must equal a 1. Okay, so we'll update our little formula here. So now we've got f prime of 1. We'll actually do a little bit of calculus here. Again, I'm kind of off to the side, and I'm just going to grab that given function, and I'm going to go derive it, and I'm going to say, f prime equals 5 minus 6x squared. And I'm just going to evaluate the derivative at x equals 1. And it looks like my final answer, 5 minus 6 is negative 1. So when I'm all said and done, the slope is going to be negative 1. Okay, in this particular example, I have changed the wording just a little bit, and this is exactly how they're going to word it on the AP exam. They've been pretty consistent over the years. And so let's go ahead and we'll see if we can dive into this one. They declared that f of x is equal to x cubed minus 2x. Again, they were very careful to give us a function that we can't actually find the inverse of. Okay, they're going to make sure that we can't do that on our own. And then they defined, just notationally speaking, they defined g of x as being f inverse. And then they said g of 4 is equal to 2. So what I said to myself, as soon as they said g of 4 is equal to 2, they're really saying to me f inverse of 4 equals 2. And then they want me to find g prime of 4. And I'm going to rewrite that myself using the notation that I used in the given formula. So when they said g prime of 4, what they're really saying is let's find the derivative of f inverse at 4. So we set up our formula, f prime of f inverse of 4. They were very nice, and they simply gave me that value. They said f prime of 4 is equal to 2. So I got to just find f prime of, let's see, make sure that's a 2. And so we just got to go find the derivative of f. A little side work here. We could say f prime is really, let's see, I think it's going to be 3x squared minus 2. And all we got to do is plug a 2 into that function now. And I would get, let's see, 3 times 4 is 12. 12 minus 2. How about a 10? So the slope at x equals 4 on the f inverse function is going to be 1/10. Now, if I had a nickel for everybody that forgot the 1 goes on top, I'd have retired already. Sometimes we get so consumed by the denominator and we just accidentally say the answer is 10. We want to make sure we've got the 1/10 in there. Okay, last question for the night, and here's where I really think you need to try to buckle down and tackle this one completely on your own, even if it turns into an utter failure. I think it's important to really stop right now and try this one on your own, at least for a couple of minutes. Get the pencil moving, get something on paper, and just force yourself to try it on your own, and then we'll come on back and we'll discuss some ideas. Okay, so on this particular one, they defined f right here. They tried to spice it up with that E term in there. Of course, G is designated as the inverse of F. And now here's the kicker, which you got to pay attention to. The point 0.01 is on the graph of F. So what I said is that means F of 0 equals 1. In other words, F inverse of 1 must equal 0. Okay? And the other thing is, as soon as they said G prime, I went ahead and I rewrote it as the derivative of F inverse. I always try to rewrite it in this form because it fits my formula and it's what I'm most comfortable with. And then we'll just say 1 over F prime of F inverse of 1. And we know that F inverse of 1 is a 0. And so now I just need to calculate F prime off to the side here. A little side work. F prime is actually 3 plus e to the x. And if I plug a 0 into that rascal, I'm going to get 4. So my overall slope is 1/4. And they could even take it a step further. Why don't we do that? What if we tried to write the equation of the line tangent to G at x equals 1? We could certainly do that. And we could say the tangent line is y minus 0 equals 1/4 quantity x minus 1. And that would be the equation of the line tangent to F inverse, or tangent to G when x equals 1. So good luck. Bring this formula with you tomorrow. We'll be ready to jump in and start a big week. So see ya.